Microspectroscopy. My name is Peter Troost, and on behalf of Zytec and our partner Advanced Technosales, we would like to welcome you. First, just a couple of housekeeping items. If you're calling in over your phone, please mute it during the presentation just for background noise. Please ask questions via the chat tool. We'll answer as many as possible at the conclusion of the presentation, and if we cannot answer your question by the end, we will certainly get back to you via email or a phone call. This webinar will be available on our website, www.zytec.com, in the coming days. Our presenter today is Dr. David Shearing. Dave is a founder and principal here at Zytec and continues to be a contributor in the development of authored over 25 papers on various aspects of vibrational spectroscopy and holds a PhD in analytical chemistry from the University of Miami in Ohio, where he is also an adjunct professor. With that said, I will turn the presentation over to Dr. Shearing.
Thank you very much, Pete, and thank you all for being available to listen to our presentation today. I also want to recognize my co-author, Tony DiDomenico, who did most of the work that you'll be seeing today. So first, we'll talk about what we're going to talk about today. Very briefly, we're going to review infrared spectrum. Briefly, we'll talk about the Surveyor, which is an FTIR microspectroscopy instrument that we use to collect all of the infrared spectroscopy data that we're presenting. Next, we'll present to you some of the tools that we use to prepare and present samples to the instrument, and also some of the sample analysis modes that we can employ to simplify and collect high-quality infrared spectra from micro samples. Lastly, we'll demonstrate some of the analysis results that we can expect to get using these methods. So, infrared spectroscopy involves the vibration of molecules, and in this figure on the right-hand side in the movie, we see two of the vibrational modes of water and the absorption bands in the spectrum that are due to the coupling of the infrared radiation with the electric field of the molecule as it vibrates. At these specific vibrational frequencies where the infrared radiation is in resonance, we will see an increased vibrational amplitude and the absorption, the transfer of energy from the incident field to the molecule. So these areas where peaks are observed are very characteristic of a molecule of interest, very highly specific, and is extremely useful in characterizing materials. So in the normal mode of operation, infrared spectroscopy is a bulk technique, and we measure the mass in which we're able to analyze materials in milligrams, the size in millimeters. Coupled with beam condensing optics, we can extend the range of measurement into the micro domain, where we can measure masses as small as the picograms mass range, and samples that are micrometers in dimension, that come close to the wavelength of light that we utilize in the spectrum. Microscopy, microspectroscopy, we tend to use those words interchangeably, allows you to characterize or identify something which is small. By coupling a microscope with infrared beam condensing optics, we're able to view disparate areas of the sample, isolate them for measurement. It's non-destructive, and as we said in the previous slide, the IR spectra are very rich in their detail and can provide an identification or allow you to elucidate functional group information from the materials that you're characterizing. Shown in this picture on the right-hand side is a very simplistic view of the power of microspectroscopy. Here we have an aluminum substrate measured in reflection, and the corresponding spectra show that these areas are chemically disparate. You could look at the details in the spectra and see differences due to the pigment and the other additives in the binder. The applications of infrared microspectroscopy are very, very diverse and include problem solving in manufacturing, defect analysis, analysis of contaminants on various different products or substrates, art authenticity or conservation and forensic, and so on. So as we said in the beginning of the presentation, we utilize the surveyor. So the surveyor is different than most FTIR microscopes, FTIR microspectroscopy systems, in that it interfaces to virtually all FTIR spectrometers. It's customer installable and can be removed, taken in and out of the sample compartment. It receives all of its power and data connection via a single USB connection, USB 2.0. Also with the system, we've developed a clip-on diamond attenuated total reflection element that allows you to record spectra and view samples through the diamond ATR element. It has a very large depth of field of view and a very large field of view, which makes it easier to locate samples. We have 3 infrared measurements modes. We'll talk about that subsequently in the presentation: transmission, reflection, ATR. With FTIR spectrometers and the fact that it's sample compartment mounted, you can use the instrument's own detector and not require liquid nitrogen for cooling. And then also it's a very compact system, which makes it a portable solution as well. So one of the features that we emphasize with Surveyor is our illumination options, which include reflected light illumination, transmission illumination, but also oblique or dark field illumination, which is especially useful with many practical samples. It's useful with samples that scatter, like this paint chip that you see on the left-hand side, and you can see that these images appear against a dark field, and that there's excellent color contrast and very good images, even through our ATR crystal, which brings up the next subject. So what we've done with Surveyor, which is a little bit different than most systems that you would encounter, is that we employ a single crystal synthetic diamond as an attenuated total reflection element. And we can also view specimens through that element that allow us to locate them and ensure confidence in hitting the mark, as it were. We also can visualize contact. So on the right-hand side, you see this wetting effect, where this micro bead has content that it minimizes sample preparation for appropriate samples. And it's also a surface selective technique. So for some samples, we can actually measure a particle or a defect on a surface selectively without measuring the spectrum of the underlying surface contribution. With Surveyor, we employed integrated video microscopy software that we call eSpot, and this allows us to control some of the features of the system, including the targeting aperture dimension, which you see in the graphic. So this is a 100 micron aperture on a Kevlar fiber, which is viewed in transmitted light illumination in this case. We also can control our infrared modes of life and analyze and document our images and save them to disk as either a TIFF or a JPEG file. So now let's segue into microspectroscopy sample preparation, which is one of the most important aspects of microspectroscopy practice. So the quality of the spectrum that you get out of a microscope, FTIR microspectroscopy system, is very much dependent on the preparation of the sample. And one of the more important issues in sample preparation is sample thickness. So it is a common issue that samples can be optically thick, bands can be totally absorbing, and therefore limited in your ability to actually determine chemical composition. So we want to make sure that we present a sample or measurement that has appropriate thickness. Sample preparation begins with kind of the physical nature of the sample, its size, its hardness, if it's a contaminant, if it's a material that's multi-phase, what are the other components and properties of those materials. So these are some examples which show kind of the diversity of samples that one might encounter in FTIR microspectroscopy, including solid crystal mixtures. This is an embedded impurity in paper. Many times we would like to measure specimens like this with ATR because we don't have to prepare the sample. But also many times, this is also the case, you can see fibers are actually extending over this impurity. So this impurity is embedded. And these types of impurities actually need to be excised from the substrate and prepared separately and measured outside of its particular substrate. Here's a defect in a polymer packaging material, and this is just a fiber on a glass fritted filter. So this was a sample that was filtered from liquid, and you can see that it's residing on the surface of the glass in this case. So an indispensable tools in preparing samples, stereo microscope, both fine tips for moving and manipulating smaller samples, and blades, some sharper than others for cutting and sectioning. So this is a very simple kit which would provide most, if not all, of the tools you would need for basic practical infrared microspectroscopy sample preparation. As I said, a stereo microscope is indispensable. Stereo microscopes come in many shapes and sizes and capabilities in terms of magnification, working distance. Do you have a camera port? Do you want to record images or movies under your stereo microscope? You can get a stereo microscope like this one, which perfectly to prepare most of what one would need to prepare samples, and you can get these for a couple of $100s. More sophisticated systems like the Leica system shown on the right-hand side cost several $1,000s, but have a much larger range of magnification, more working distance, more flexibility, and a camera port to record images if you so desire. We need greater than 30x magnification in our stereo microscope to handle samples that are smaller than 100 micrometers. That's an important thing to remember. Probes and forceps are indispensable in moving and manipulating samples. This moving and manipulating samples sounds like a daunting task to do, and you can manipulate samples that are as small as 10 microns or even less with the appropriate tools. And one of the main things in manipulating smaller samples is the fineness of your probe or your forceps. The finer the tip, the smaller the sample you'll be able to manipulate. And a particularly fine tip probe are those that are fashioned from tungsten needle probes. So these can both be purchased or made from tungsten wire. It's a fairly simple process to make an extremely fine pointed tungsten needle probe from tungsten wire and sodium nitrite. Heating it in sodium nitrite will etch the tungsten and make a very, very fine tip probe, which then you can put into these, what we call pin vices. And this will allow you to manipulate and move really extremely small samples. We also need sometimes to cut samples, and various blades have different sharpnesses. Very sharp blades are needed to cut some samples. The X-Acto blades that are exhibited in the roller knife and this X-Acto knife actually are not particularly sharp, relatively speaking. So a scalpel blade or actually a double-edged razor blade, which you have to be very, very careful in using, are much sharper actually than an X-Acto blade and can be more useful with samples that require a very sharp blade, for instance, a soft rubber sample. One thing that we did not mention or show a picture of in the presentation that I want to point out right up front is that common 1x3-inch glass microscope slides are indispensable substrates for sample preparation. They cannot be used for infrared microspectroscopy analysis as substrates. However, they are very inexpensive, disposable substrates that you use in the initial manipulation and preparation of samples before transferring those samples to an appropriate substrate for infrared measurement. What I'm showing you on this slide are a couple of substrates that are useful for infrared measurement. And the first is a glass microscope slide, which is actually more than 99% reflective to IR light. This can be used for samples that are fairly thin, or samples that are deposited from solution onto the substrate. And one can measure samples in a reflection mode, a double path reflection mode. These are standard 1x3-inch format and can fit into the sample clip of the microscope. They are easily scratched, which is a downside, and they're not recommended for ATR measurements without further support because they're fairly thin and delicate. One of the most useful techniques or substrates for FTI or microspectroscopy measurements is the low E glass slide. Low E glass is a glass substrate that's coated with a very thin film of silver, very transmissive to visible light, so we can observe samples in all illumination modes, oblique, reflected, and transmitted light. But we're measuring the sample in the infrared via double pass reflection. So as with the gold microscope slide, we have to have an appropriate thickness of our sample to get good data. This is also a very good substrate for ATR measurements because the slide is thicker, and with the maximum force that we recommend applying via the diamond, which is about 15 pounds, these slides hold up over that entire range of force. We also can put transmitted light substrates, whether it's infrared crystals or diamond windows, into 3-hole slide mounts. And these accept the 13-millimeter diameter infrared transparent windows. Compression cells, and this is an example of a compression cell, can be used for flattening or holding materials flat over the entire field of view. Some samples will have a tendency to not lie flat, and therefore pieces of the sample will be in and out of focus depending on where you're at on the sample. So if you have a transmission compression cell, like the one shown, you can hold the samples flat over the entire field of view. And also, particularly with diamond windows, you can do some further flattening of the sample in the cell to get an appropriate path length. In transmission, so it can be can be easier to prepare samples of appropriate thickness because you only have one path through the sample. And typically with layered samples, those are measured in transmission, and many times paint chips and so on are measured in transmitted light illumination as well. Transmitted light infrared spectroscopy, I should say. So some of the infrared windows that we can use in a compression cell or a 3-hole mount slide. Potassium bromide is a general purpose material. It is transmissive through the entire range of the instrument and the detector mounted in the instrument. They're fairly fragile and hygroscopically. Zinc selenide is harder. It is water insoluble, so if you're working with wet material, you might want to use a material like zinc selenide or barium fluoride. And the downside of zinc selenide is that you can see it's a yellow color. Diamond is a very strong chemically resistant substrate. We can prepare samples on diamond without transferring them. In other words, the sample manipulation procedures that we're going to demonstrate later can be done on a diamond substrate, including thinning the sample with some fairly aggressive force. You won't scratch the diamond, and diamond is chemically inert with anything that you would want to use for cleaning. And the spectral range extends from the far infrared all the way up into or close to the UV, so we can actually obviously observe samples in transmitted light, illumination, reflected light, illumination, etc. The diamond windows that we fabricate fit within that 13 millimeter diameter size, so it's interchangeable in the cell or the 3-hole slide mount with these other infrared substrates. So with multi-layered samples, there are various methods that you might want to use for sectioning. And in layered samples, some of these layers can be extremely thin, 10 micrometers or less, which can challenge infrared microspectroscopy analysis, making these thin layers thicker effectively and easier to analyze. So a microtome is a fairly sophisticated instrument that takes some training and technique to master. They can be relatively costly, but they can be both automated and manual. There are lower cost, less flexible options for sectioning. Shown on the bottom is the Easy Slicer, which allows the sectioning of samples from 0 to 45 degree angles using a circular blade, which using the knob here, you actually translate that blade over your sample, and you can also control the sample size of sectioning. An even lower cost option is the slicer attachment to the microbite, and these come with attachments that allow you to section samples at 0 to 15, or I'm sorry, 30 or 15 degrees angle using a simple blade. So it's a little bit harder to control your thickness with this method, but it's a very inexpensive solution. So there are other miscellaneous tools that one could invest in to help simplify analysis. One is a microvise, and a microvise is useful for oddly shaped that you want to hold in a particular orientation. So it allows you to grip the samples, and it interfaces into the standard 1x3-inch stage clip. The MicroTouch pen allows you to pick up small samples. It has a very small adhesive tip, and when this tip retracts, the sample drops onto the desired surface. If your hands are not steady, there are various micro manipulator options that incorporate imaging as part of the micro manipulator. Very expensive solutions along these lines are available that completely automate the process of moving and transferring samples, and can be used to transfer extremely small samples. Is used. So as we said in the introduction, the surveyor and other microscopes have the ability to measure samples in attenuated total reflection mode, or transmission. How do you choose the best sample measuring technique? This really many times depends on the sample itself. So attenuated total reflection is useful both in terms of minimizing sample preparation. For some samples, it may require no preparation, but it requires you to physically touch the sample. And also, an advantage of attenuated total reflection is that the sample thickness is determined. The sample thickness is determined by the refractive index ratio of your sample to the ATR element. So that's very helpful in sample preparation and getting a very representative path length of sample for infrared analysis. However, the size of sample that you can measure is larger, effectively larger, with attenuated total reflection. You can measure smaller samples with reflection or transmission infrared. In reflection, as we mentioned, light passes through the sample, reflects off an underlying substrate, and back through the sample. For some samples, it can be hard to thin the samples to the extent required to get an appropriate path length using reflection in infrared. An example, without actually having something to compress the sample, it can be very difficult to get that sample to a thin enough sample size. In transmission, light passes through the sample one time, so the thickness can be smaller due to that. And as we said earlier, we can compress samples and thin them into a sandwich configuration to get that appropriate path length. So these are some samples that can be measured with ATR. On the left-hand side is actually a contaminant on the surface of a pharmaceutical, which is observed through the diamond ATR crystal. And in this case, we were able to selectively measure that. Another on the right-hand side, this is a microplastic that was from filtered water from the Hudson River. And this was moved and transferred to a Lowy glass slide and measured in ATR mode. So these samples in ATR are generally larger than 100 micrometers in dimension. Mixtures can be a common issue in microspectroscopy samples, and multiple methods exist for separating and analyzing these different mixture components. In fact, infrared microspectroscopy is very powerful in its ability with the microscope from the observation, from the microscopy observation, inferring that these materials are of different composition simply because they're of a different habit. And this is called Pasteur separation, separating particles by different appearance or habit. So this is a mixture analysis performed with micro ATR, a mixture of citric acid and sucrose. And via the microscopy, we're able to differentiate the different crystals based on their habit. Particle 1, which is citric acid, is circular or spherical, spheroid shaped crystal. Sucrose is more rectangular or cubic in its habit, and we could selectively touch these crystals. We're observing them on Lowy glass slide with oblique illumination and measure the spectral contribution of these materials separately. In the very top spectrum is the spectrum of a mixture of sucrose and citric acid. So in reflection, this is not attenuated total reflection now. This is reflection absorption, measuring by reflection of a sample that's on a reflective substrate. In some cases, or no sample preparation because it's on a reflective surface, a metal. Of course, gold is the most reflective, but other surfaces that, stainless steel, aluminum, even other metals are highly reflective, and samples on them are amenable to infrared spectroscopy analysis directly. So on the left-hand side slide, there is a contaminant film right in here that was observed on a metal surface. This was a product problem where there was contamination on these metal parts, and we collect the background off a clean section, a reference spectrum off a clean section, and then a ratio spectrum off of the contaminated surface, and we're able to get a spectrum of that material directly. We can also transfer samples to reflective surfaces. So this was this red fiber we showed you before was on a glass filter. As it turned out, this glass filter contributed a contribution in ATR mode. So we removed the fiber from this glass filter substrate and transferred it to Lowy glass. So now we're observing the specimen in transmitted light, bright field illumination, but we flattened a portion of this fiber out, and now we're able to measure it with reflection on this Lowy glass substrate as we observe the sample in transmitted light illumination. I should say that the Lowy glass substrate, and so that's an advantage over some of the more cost-effective infrared substrates. KBR, zinc selenide are not durable enough to flatten samples directly on the substrate. So they need to be flattened before placing on the substrate and then measured there. So we're going to show a movie of the procedure, basically, of how you transfer and flatten a material to make it an appropriate path length for infrared spectroscopy analysis. So first we're going to locate. You can see that there are multiple samples on this substrate. We are going to target one of the fiber samples with a fine tip probe. So we're going to go in and get the red one. You see, just by touching the sample through electrostatic interaction, it is on the probe. Next, even though this fiber is very thin, it is optically thick. So for the best quality spectra, we want to thin it and get an appropriate path length. We use a device that I showed earlier called the roller knife. Then we're able to measure the spectrum of that material with very high quality. The red spectrum in the top is the spectrum measured in reflection from Lowy glass compared with a polyethylene terephthalate fiber on the bottom. So the bands are on scale, would be perfectly amenable to a spectral library search method or functional group analysis through expert spectroscopy practice. So multi-layered samples, or as I said before, samples which can be difficult to thin and are not amenable to ATR analysis, can be measured by transmission. And this is a multi-layered packaging material, and you can see that it has 2 layers. This was sectioned actually with a scalpel, and then put into a compression cell with KBR windows in this case to hold it thin and in focus across the field of view. With a microscope, we just targeted these separate areas. You can see that we have a white layer and a clear layer on the spectra on the right, shown in transmission. We can see that the material in both cases is polyethylene. However, in the case of the white layer, there's some additives, probably titanium dioxide, but other materials as well that are probably part of the pigmentation of that particular sample. Another aspect in transmission analysis is that many of the commercial spectral databases are actually transmission libraries. So that can be a factor in selecting a technique for analysis. There are many more. Many of the libraries are transmission libraries. So lastly, we're going to show you an example of a relatively simple sample, but in terms of observation, but fairly complex sample analysis, and that's the paint chip. So paint chips are multi-component, or paints are multi-component materials that consist of binders, pigments, other additives, either fillers or extenders, and to analyze all of the components of a paint, which can be important for art conservation or authenticity or in forensic analysis, takes a little bit of technique in analyzing complex samples. So here we have a red commercial paint, which is imaged. This is an artist's paint in this case, which is imaged with oblique illumination. We measured the chip in reflection mode, in this case with 160 micrometer aperture, and the sample is fairly thick. We do see decent band definition, but nevertheless the bands are fairly broad, particularly these strong bands, and the sample is a little thick. So what we can do is use some on-slide solvent extraction methodology. So this takes a little bit of practice, experience, and testing, but we can gently heat the material with ethanol solvent, and some of the material will be transported from the very particular region of the paint chip. And so we've gone over to a region where some of the sample was obviously transported. We have a film here, and we come in and measure a very high quality spectrum in the red, very good sample thickness of the binder material, which is consistent with a vinyl acrylic copolymer material. So in this case, we're measuring material that is separate from other materials in the paint composition. If we go back to the paint chip in this area where we've extracted the binder away, we can get a contribution which is mostly due to the pigment, which is consistent with pigment. Although that paint chip was very, very brilliant red, the concentration of pigment is actually quite low, and we cannot see much contribution, if any, from the pigment in the spectrum of the paint chip, which has not undergone this kind of separation or manipulation. With that, I'd like to conclude and would be happy to answer any questions that we have in the time that we have available. And if you would like to contact us separately, here is all of our contact information, and we'd be happy to converse with you regarding your problems.
Hi, Dave. One question came in. You mentioned the surveyor does not need liquid nitrogen. What kind of detector does the surveyor use?
So the surveyor is different than all, I would say, it's true to say, all microspectroscopy instruments on the market, in that it uses the instrument's own detector. So in most cases, the instrument has an instrument-mounted DTGS detector, which comes with your spectrometer. And all of these spectrometers you see on this image now being displayed from the various different vendors, all of these have DTGS detectors installed in the instrument, MCT detectors, which are more sensitive and require liquid nitrogen cooling. So the surveyor can also be used with those instruments too, with those detectors, because it uses the instrument-mounted detector, the detector that comes with your FTIR. The surveyor itself does not have an infrared detector installed in the instrument. It utilizes the instrument-mounted detector.
Great, thanks, Dave. And another question is, what are the benefits again of having the view through ATR?
The benefits of having the view, you're able to observe the sample through the ATR with the microscope, visually, optically. You can record images through the ATR, and you can center and focus your image looking through the diamond ATR element. The other materials that are utilized in ATR, germanium is common, silicon is common for FTIR microscope systems. You cannot see through these, so you have to observe and focus your sample with the ATR crystal out of place, not in the field of view. And then you either have to slide it in or push it down. It depends on the design. And when you do that, you're no longer able to observe your sample. So the simple answer to that, you have confidence that you're hitting the sample. With those other ATR crystal materials, even if you're measuring a spectrum, you're blind and you're not 100% confident that you're hitting the sample area of interest. Also, what I didn't mention is that with the diamond, you can observe the sample contacting the diamond surface as well, wetting the surface of the diamond. So that gives you added confidence also that you're measuring the sample area of interest.
Thank you. And one more question is, how does the surveyor compare to a more traditional IR microscope? One that, maybe from Thermo or PerkinElmer.
I think the main differences are that it is customer installed and removed, so you can use it when you need it. It's not permanently mounted. It can be permanently mounted. You just leave it in there. So that's one aspect of it. I think that it's relatively simple to use in comparison. It's much like a microscope you'd use in a high school or freshman biology class in terms of the microscope controls. So it has, as I said, a large depth of field and a large field of view. Those are different things, but both of them are ease of use features, which allow you to locate samples more easily, and valuable tool on a relatively low-cost platform. Diamond ATR on permanently mounted FTIR microscope systems can be almost as much to purchase as is the Surveyor. So you're getting that that value in a very economical package.
Awesome, awesome. Well, thank you. Thank you all for attending. This concludes our webinar for the day. Again, if you have any follow-up questions, there's contact information on the last slide. And certainly this webinar will be available on our website in the very near future. Thanks again and have a great day.